Why do we love to be mean? In fact, why do we love the mean? The arithmetic mean, the geometric mean, the golden mean, the harmonic mean? What does it all mean? If you thought I was going to be talking about feelings and emotions, you're wrong. I'm going to be talking about statistics. But hopefully I'll do it in a way that doesn't completely bore you. Today I'm going to be talking about two particular definitions of what an average is. The arithmetic mean and the median. And I'll be trying to convince you that the median is actually something worth considering. So first of all, the arithmetic mean. Most commonly it's used as an average in the sense of being a sample mean. And the very first history of the arithmetic mean in this sense, or the sample mean, is actually long-winded and very detailed and meticulous. The Indian culture, the Chinese culture, and the Greek culture all have examples of using it. Aristotle is probably credited with being the first person to actually codify it in writing, and had a lot to say about mostly the mean between two numbers, so kind of the average between two numbers. And throughout history, it's been used with more and more frequency to estimate what the average of something is, and it's for a good reason. It turns out that during the 17th century, a lot of mathematicians started to look at different probability distributions, different data sets when you have more and more of these numbers that you're collecting. And for a lot of the very simple, very well defined, and very well behaved distributions that we know of and that we have, the arithmetic mean, which is just taking a bunch of numbers, adding them up and dividing by however many numbers you had, kind of falls out as the optimal estimate of what the mean of that distribution is. So it's kind of a nice result. The other nice result is in the minimization of the mean square error sense. The arithmetic mean actually also happens to be the optimal estimate. So in many statistical and mathematic results, everyone was really happy. This is a really nice property to have. So it's kind of this natural thing to do. It's kind of the most simple, most obvious answer when you're trying to average things and get an estimate for the sample mean. But maybe it's natural because we've kind of been taught that it's natural, right? In the past 2 centuries, we've only really been dealing with very simple distributions, the most common of which is the normal distribution, which everyone kind of probably knows, right? It's the bell curve. It kind of goes like this. And the characteristic of the bell curve is that you have very few outliers past about 3 standard deviations, and most of your samples are kind of in the middle, right? But it turns out that a lot of real-world data doesn't behave this way, and that the distributions that we've defined up to a general order of estimation are accurate, but as we're getting into the modern age where we want things to be very accurate, they all don't make any sense. It turns out there's a lot more of these outliers that we have to be worried about in most real-world data than these typical distributions account for. One of the most hilarious distributions is the Cauchy distribution, which looks almost exactly like a normal distribution, but the tail end is just a little bit higher than what the Gaussian is. And when you actually start to analyze it, it turns out that it has no mean, it has no standard deviation. Both of those are indeterminate, they're infinite. So the kind of hilarious result of this distribution is that because the mean is infinite, you can actually take one single sample from this distribution, compare it to the arithmetic mean or average of 1,000,000 samples, and the predictive power of both of those is exactly the same. Both of those pieces of information tell you the exact same thing about that distribution, which is that the mean could be anything. Enter the median. Exactly 1599, an English sailor by the name of Edward Wright started looking at compass readings as they were sailing around the world, and realized that if you take a bunch of compass readings at different parts of, a short part of the voyage, and you average those together, there's a good chance you're going to be off by quite a bit, because every once in a while you'll get a reading that's really, really deviated from what the actual number is. So he invented this idea of the median, where he would just take a bunch of readings and then take whichever one the middle value ordered from lowest to highest was and say that's the actual number. And if you think about this, this makes sense, right? If you have, the simplest example is if you have something like housing prices. If you have a couple homes that are in an area that are 100,000, 120,000, 130,000, and then in the same neighborhood you have a house that's like $5 million, way over here. What's the average? Somewhere around here, 300,000. Does that really reflect the actual value of houses in that neighborhood? No, it doesn't. So the median started becoming a more useful measure of statistics during the last century, as people in economics and sociology realized that a lot of these average arithmetic mean measures were not very indicative of what the social situation was. And this is a particular hot topic right now, where in 1980, the Bureau of Labor Statistics decided to not only post the average income for people in the US, but also the median income. And that's where you see a lot of these debates over the last few recessions, economic crises, because the average income in the US has slowly gone up, but the median income has actually stayed flat and in some cases decreased, which you can kind of see in those arguments talking about how the rich are getting richer while everyone else is just kind of getting by. So the median is useful in some of these economic metrics. It's also very useful in a field that's very close to my heart, which is signal processing. The median filter is one of the more interesting and more basic of the adaptive filtering methods that are used in that field. And really this goes to the crux of the signal processing and sort of engineering issue, which is that modern information, modern data is much more complicated than what we used to have. Engineers these days can't design things that assume the data is going to be pretty, it's all going to be sort of clustered nicely, there won't be any of these crazy outliers one way or the other. And so in order to counteract that, you actually have to start using the median rather than the mean. So what's the point of all this? What does this all mean? Mean. The median is a useful metric, and in today's society, with more and more complicated data, where we're not comparing having a good estimate with having a good estimate, but we're comparing having a good estimate with an excellent estimate. The median is the way to go. So don't be so fixated on the mean. And also, don't be mean. Thank you.